Association rules and notes. An association rule is an implication of the form x to y, where x is the antecedent and y is the consequent of the rule. One example of association rules is in a basket analysis where we want to find the dependency between two items x and y. The typical application is in retail, where x and y are items sold, as we discussed in a section 1.2.1. In learning association rules, there are three measures that are frequently calculated. Okay, support of the association rule x imply y. Support xy is equals to defined as the probability of xy, which is, by definition, is the number of customers who bought x and y divided by the number of customers. Okay, now the second measure is the confidence. Confidence of the association rule, x imply y. Confidence of x imply y is equals to, that is defined as the probability of y conditioning on x, that is the probability of xy divided by the probability of x. That is the number of customers who bought x and y divided by the number of customers who bought x. Okay, the third measure is the lift, also known as the interest of the association rule, x imply y. That is, lift of x imply y is equals to the probability of xy divided by the probability of x and times the probability of y. That is, the probability of y conditioning on x divided by the probability of y. There are other measures as well, but these three, especially the first two, are the most widely known and used. Confidence is the conditional probability, P of y conditioning on x, which is what we normally calculate. To be able to say that the rule holds with enough confidence, this value should be close to 1 and significantly larger than P of y, the overall probability of people buying y. We are also interested in maximizing the support of the rule because even if there is a dependency with a strong confidence value, if the number of such customers is small, the rule is worthless. Support shows the statistical significance of the rule, whereas confidence shows the strength of the rule. The minimal support and confidence values are set by the company, and all rules with higher support and confidence are searched for in the database. If x and y are independent, then we expected lift to be close to 1. If the ratio differs, if the probability of y conditional on x and the probability of y are different, we expect there to be a dependency between the two items. If the lift is more than 1, we can say that x makes y more likely, and if the lift is less than 1, having x makes y less likely. These formulas can easily be generalized to more than two items. For example, the set XYZ is a 3-item set, and we may look for a rule such as XZ implies Y, that is the probability of Y conditioning on XZ. We are interested in finding all such rules having high enough support and confidence, and because a sales database is generally very large, we want to find them by doing a small number of passes over the database. There is an efficient algorithm called a priori, Aguirre et al., which derived in 1996, that does this, which has 2 steps. 1. Finding frequent item sets, that is, those which have enough support, and 2. Converting them to rules with enough confidence by splitting the items into 2, as items in the antecedent and items in the consequent. 1. To find frequent item sets quickly without a complete enumeration of all subsets of items. A priori algorithm uses the factor that for the set x, y, z to be frequent, have enough support, all its subsets, the set xy, the set xz, and the set yz should be frequent as well. Adding another item can never increase support. That is, we only need to check for 3 item sets, all of whose 2 item subsets are frequent. Or in other words, if a 2 item set is known not to be frequent, all its supersets can be pruned and need not be checked. We start by finding the frequent 1 item sets, and at each step, inductively from frequent k item sets, we generate candidate k plus 1 item sets, and then do a pass over the data to check if they have enough support. The priori algorithm stores the frequent item sets in a hash table for easy access. Note that the number of candidate item sets will decrease very rapidly as k increases. If the largest item set has n items, we need a total of n plus 1 passes over the data. Once we find the frequent k item sets, we need to convert them to rules by splitting the k item sets into 2 as antecedent and consequent. Just like we do for generating the item sets, we start by putting a single consequent and k-1 items in the antecedent. Then, for all possible single consequents, we check if the rule has enough confidence and remove it if it does not. Note that for the same item set, there may be multiple rules with the different subsets as antecedent and consequent. Then inductively, we check whether we can move another item from the antecedent to the consequent. Rules with more items in the consequent are more specific and more useful. Here, as in item set generation, we use the fact that to be able to have rules with the 2 items in the consequent with enough confidence, each of the 2 rules with a single consequent by itself should have enough confidence. That is, we go from 1 consequent rules to 2 consequent rules and need not check for all possible 2 term consequences. This is in exercise 7. It should be kept in mind that a rule X implies Y need not imply causality, but just an association. In a problem, there may also be hidden variables whose values are never known through evidence. The advantage of using hidden variables is that the dependency structure can be more easily defined. For example, in a basket analysis, when we want to find the dependencies among items sold, let us say we know that there is a dependency among baby food, diapers, and milk, in that a customer buying one of these is very much likely to buy the other 2. Instead of representing dependencies among these 3, we may designate a hidden node, baby at home, as the hidden cause of the consumption of these 3 items. Graphical models that we will discuss in Chapter 16 allow us to represent such hidden variables. When there are hidden nodes, the values are estimated given the values of observed nodes and filled in nodes. Making decisions under uncertainty has a long history, and over time, humanity has looked at all sorts of strange places for evidence to remove the uncertainty: stars, crystal balls, and coffee cups. Reasoning from meaningful evidence using probability theory is only a few hundred years old. See Newman, 1988, for the history of probability and the statistics, and some very early articles by Laplace, Bernoulli, and others who have founded the theory. Russell and Norwich, 1995, give an excellent discussion of utility theory and the value of information, also discussing the assignment of utility in monetary terms. Schaffer and Pearl, 1990, is an early collection of articles on reasoning under uncertainty. Association rules are successfully used in many data mining applications, and we see such rules on many websites that recommend books, movies, music, and so on. The algorithm is very simple, and its efficient implementation on very large databases is critical. Later, we will see in Chapter 16 about graphical models how to generalize from association rules to concepts that need not be binary and where associations can be of different types, also allowing hidden variables.